Okay, so today we're going to be looking at question 19. This is going to be from chapter 21, from matter and interaction. That's going to be this question here. Be careful and look at this figure here because it's going to be super important to what we're dealing with. This is the question here, but I'm going to type that up and put that into put it into the comment section so you can have that to refer to during the time. And this is my work here, just kind of simplified version of what's going on. And so we know that we're going to be messing with Gauss's law, and so Gauss's law is going to be up here at the top. That's going to be his law, which is going to be equal to Q of the inside over epsilon naught. And then we know that the electric field dot n hat times dA is going to be equal to E dA cosine of theta, and cosine of theta is 0, so the whole thing's going to be 0. Then here we're going to be doing some integration, and this will all be referenced into part A whenever they're asking us to find the magnitude of the field in the air gap. That's kind of what we're doing for this top part here. And so we need to find, we need to integrate E dA because n hat is 0. And so that's going to give us with A. And so the area of the box. So next we want to find the charge. The charge of the inside is going to be equal to Q over A times the area of the box. Oh, and I forgot to mention that here, well, I put it both places. The integral of dA is A box. And then we're going to use Gauss's law here. And we're going to take E times the area of the box is equal to Q over A times the area of the box over epsilon naught. We're going to plug in A for that. And just simplify that and solve for E, and this should be the answer that you get there. Don't forget that the flux emerges normally from the surface of the plate of the capacitor, which is why the cosine is 0. And so that's super important there. Oh, and don't forget that this is only in region 1 that's going to be found. So in part B, we know that the region 2, which is what we're looking at, is going to be totally inside of the gap. So we need to assume that the electric field to be varying, and we'll decide if that's going to be true or not. We know that the electric field, due to the negatively charged plate, is going to be given by Q over A E sub naught and Q over A E sub naught for the positive charge as well. And we know that the electric field in region 2 within the plates is constant. And we see that from right here because they are the same. And they're both facing towards the negative plate. So we know that. And for part C, we know that we're going to be looking at region 3, which is partially inside the plate. And it's going to have the charge of negative Q. And so this is going to be similar to the case before. The flux is going to be coming through the parallel plate to the surface, and then it's going to be perpendicular surface, so we know that that's going to be 0, and there's no flux that's going to enter the face because of the conducting plate, and so we know that E is equal to Q over the area times epsilon naught, which is the same as all. And then we have part D back here, which we were asked to find using the fringe field. Find the charge of Q. So this is going back to Gauss's law, and then we're going to find the Efringe field is equal to Q over A to epsilon naught. And so S over R, and you're going to simplify that, and then you're going to multiply it times the area, which is going to equal to Q over epsilon naught, which is going to be exactly what we did here for Gauss's law before. And then you're going to simplify all that, and then you should be able to get Q over A over 2 epsilon naught S over R times the area is equal to Q over epsilon naught and solve for that Q, and you should get approximately Q over Z is times S over R, and so that should be the charge of the outer surface of the plate. That's going to be about the approximation that we're going to use.